Next example 2.17. A long charged cylinder of linear charge density lambda is surrounded by a hollow coaxial conducting cylinder. What is the electric field in the space between the two cylinders? Now see here, a long charged cylinder of linear charge density lambda is surrounded by hollow coaxial conducting cylinder. Here we consider the length of the cylinder, that is equal to L. Now see this inner cylinder, that is with radius equal to A, and that particular cylinder is charged 1 and linear charge density for that cylinder is lambda. Then the outer cylinder, which one is coaxial one to the inner one, that is with radius equal to B. Now we want to find the electric field in the space between these two cylinders. So for that, consider a cylindrical Gaussian surface having radius equal to small r. Now, if we consider the cylindrical Gaussian surface here, then we can understand this thing. The flux will be passing through the cylindrically curved surface because the electric field that will be from inner cylinder to outer one. Okay. Now suppose here we consider infinitesimal small surface element at the cylindrically curved surface, then its area vector perpendicular to it, ds, that will be as shown in this figure, and electric field that is radially outward. So at that particular surface element, the area vector and electric field both will be in the same direction. Clear up to this one? Now, as per Gauss's theorem, flux phi, that is integration E dot ds, that is sigma q upon epsilon 0. Now E and ds both are in the same direction. So integration E ds cos theta, that is cos 0, that is 1. And magnitude wise, the electric field at each and every point on the cylindrically curved surface, that will be same one, because each point that will be at the same perpendicular distance r from the axis. So we can write E integration ds, that is equal to sigma q upon epsilon 0. Now integration ds, that will give you the total cylindrical surface area. So that is 2 pi RL. So we can write the left hand side E into 2 pi RL. Now charge enclosed by this Gaussian surface. So here the length of the cylinder under consideration, that is L, and linear charge density, that is given to U lambda. So we can write when charge per unit length is lambda, therefore charge in length L is how much? So that is lambda into L upon epsilon 0. So resultantly we will get electric field E, that is equal to lambda upon 2 pi epsilon 0 R. Clear to all of you? Now here if we consider this system of two coaxial cylinder as a capacitor, then For this cylindrical capacitor, we can derive the equation for capacitance. Now, the potential difference between two cylinders that we can give by V equal to minus integration A to B minus E dot dr. Say, we have the relationship electric field E that is equal to minus dV by dr. So dV equal to minus E dr. And therefore V equal to integration minus E dot dr that we can write. And potential difference between any 2 points that is given by the equation V that is equal to minus integration A to B E dot dr. Clear? So as per that, this equation is written here. Now, here minus minus plus E and dr both are in the same direction. So we can simply write that is E dr, and E that we already calculated lambda upon 2 pi epsilon 0 into 1 upon r into dr. Now lambda upon 2 pi epsilon 0, that is constant one, take it outside the integration. So we can write the potential difference between two plates, that is lambda upon 2 pi epsilon 0 integration A to B 1 upon r dr. Now integration 1 upon r, that is ln r, limits A to B. First we have to substitute r equal to b, the upper limit, then minus r equal to a, the lower limit. So we can write resultantly potential difference between these two cylinders, or we can say two plates of the given capacitor, lambda upon 2 pi epsilon 0 ln b minus ln a. So that is lambda upon 2 pi epsilon 0 ln b upon a. Now as per definition, capacitance C, that is Q by V. Now Q, that is lambda into L, because length of the cylinder, that is L, and linear charge density on the cylinder, that is lambda. And substitute the value of V, that is lambda upon 2 pi epsilon 0 ln b upon A. Lambda lambda cancel. So finally you will get the capacitance C, that is 2 pi epsilon 0 L upon ln b by A. Clear to all of you?